Hello, everyone. Today I'm going to be talking about what we missed in class in case you had some technical difficulties that a lot of people run in and couldn't join the Google Meet. So I'm going to go over what we did today. So to start off with, we went over some of the stuff that we did last class, which was going over all the different types of forces that we have, like friction, applied, tension, gravity, normal force. Those are our big forces. And then we also went over equilibrium and how it applies to Newton's first law. So if you remember, Newton's first law is objects at rest stay at rest. Objects moving will keep on moving unless a force is applied. So equilibrium is when there is no net force. So it's when an object is staying at rest, or it's when an object is moving at constant velocity. So if we see an object at rest, like I am right now, we know that I'm at equilibrium because I'm not accelerating. If we see an object moving at constant velocity, then that same thing is true. There's no net force on it. All right. We also, this is so starting off with some new stuff, we talked about Newton's second law. And let me move my camera so it's out of the way. Oops, grabbed the wrong thing there. There we go. So Newton's second law can be written out numerically, or sorry, not numerically, can be written out with words, which is acceleration of an object is related to its net force and resistance to motion. However, it's easiest to understand when we actually look at the formula. So what Newton's second law and what it says is that the acceleration of an object is equal to its net force divided by its mass. In other words, when an object has a net force on it, it will accelerate. And its mass actually makes it harder to accelerate, which should hopefully make some sense. It's easy for you to move a light object around, but an object that's more massive, let's say you're trying to push like a refrigerator or heavy couch, you know that requires a lot more force, a lot more effort to get to actually start moving, which is what acceleration is, it's change in speed. So it's when you have a net force, you have an acceleration, though mass makes it harder to actually get moving, get accelerating. And one final thing is I want to eliminate a misconception that's very common. So we talked about many different types of forces like force of friction, applied force, normal force, all that stuff. A lot of people start expecting net force to be its own type of force, but it's not. And here's my example of that. On this side, we have our dollar bill, nickel, net worth, dime, quarter, all that stuff. Those are all currencies except for net worth. Net worth is the sum of all of these things. While on the other hand, we have all these different types of forces, except for net force is the sum of all of those forces. And that's how that works. All right, so done with our notes. Now we're going to look at the actual worksheet. So I'm going to make my camera a little bit bigger here, okay? And what we did is I went through a couple of examples of how to make some free body diagrams, which are the drawings that we're going to be doing on the worksheet that I gave on the Google Classroom. What we did is after I went over this, we worked on those worksheets on the Google Classroom. So I did a couple of examples. The first one was an example of me. So my force diagram at this moment. So at this moment, I'm going to represent myself as a dot, as we always do for these free body diagrams. I'm going to draw an arrow down, and this is going to represent our gravity. Gravity will always be pulling us down. Anytime that we're on Earth, we have gravity pulling us down. And then I have a normal force going up. What that normal force is the force that my chair is pushing up against me. So my normal force is going up, my gravity is going down. Now you'll see I put in these little marks here and there. What those stand for is that these are the same as each other. So they're the same length. Sometimes hard to actually draw the exact same length. I'm looking at this, it looks like I drew gravity a little bit bigger, but I didn't want to do that. I wanted to draw them the same length because I'm at rest. I should be at equilibrium. All of our forces should cancel out. So these two are equal to one another. And I show that they're equal to one another by drawing those lines. All right, let's look at another example. All right, let's say I am pushing a table on like one of our lab tables and trying to push it, and what happens there. So we have a table that's being pushed. And let's say that I'm moving at a constant speed. The reason why I'm writing down that I'm moving at constant speed is because, again, Newton's first law, or definition of equilibrium, when we're moving at a constant speed, all of the forces should balance out, and I should have no net force if I'm moving at constant speed. So I have to think about that when I'm drawing my force diagram. Again, we're on Earth, so I have gravity. We're also, that table is going to be resting on the floor. I'm not picking it up or anything like that. So that's the normal force, because that's the floor. These are going to be equal to each other, because again, I'm moving at constant speed. I'm pushing it over to the side. That's going to be an applied force. And finally, if I just had that, I would be speeding up. But something is keeping me at constant speed, and that is my force of friction. And I again want to make sure that these are equal to each other. So this time I drew 2 dashes to show that these two are equal to each other, but not necessarily equal to those two. And of course you could draw 3 dashes, 4 dashes. It's just to show that, hey, these two are the same. That's pretty much our drawing for that. Finally, I think the last one I'm going to go for is, let's say, a bowling ball that I've bowled down a bowling alley. We got bowling ball. And let's say, again, that's moving at a constant speed. So we have gravity, we have normal, just like always. I shouldn't say just like always. Gravity will pretty much just like be always. We pretty much always have gravity going down. However, our normal force, that's only when something's on a surface, which is quite often that we have stuff resting on a surface. But let's say if I'm hanging something up from a string, then it wouldn't be normal force holding up, it would be tension. Okay, anyways, so these are equal to each other. Because I'm moving at a constant speed, I should have no net force. Now, if we're on a bowling alley, bowling alleys are really nice because they're basically frictionless, and we're going to assume that we're frictionless here. So there's no friction here, and actually this is it. This is our drawing. Now, a lot of people want to put an applied force forward, what's actually, making the bowling ball move. But we have to remember Newton's first law. Why is this bowling ball moving? Because it's already moving. Things that are moving will keep on moving. So at some point in the bowling ball's past, when you were actually holding in your hands and you pushed it forward to bowl it, yes, you absolutely had an applied force. But after it leaves your hand, you're no longer pushing on it. You don't have like Jedi force powers. You're not force pushing it forward. It's rolling at this point because it's already rolling to begin with. So this is it. This is our drawing for our rolling bowling ball. Nothing pushing it forward. Now I want to do one more. Let's say that this bowling ball was now on a frictioned surface and no longer moving at a constant speed. Let's say that was slowing down. So we have a force going backwards. Let's say I was doing it on a classroom floor, which has some friction, and that is our force of friction, slowing it down. So this would be an example of one that's slowing it down. Now sometimes, like this worksheet, I'm going to ask you to also draw the net force. Anytime everything cancels out, your net force you can write as non-applicable, or you can write 0. If, however, like this, we do have a net force because we're slowing down or speeding up, we should draw our net force. It would be this, and it should actually be the same length as this because the ups and the downs cancel each other out, and we're just left with a net force to the left. All right, that is everything I have. Basically, the only other thing is on the classroom, there's the worksheet that's called Simple Force Diagrams. I would like you to complete that for our asynchronous work. They started in class working together, and then they had to finish it as well. Looks like you guys will just have to finish it. And then also the textbook work, some people didn't quite finish that up. Make sure you have that done as well for our asynchronous work. And that is pretty much it. I hope you have a good day. Sorry about the technical issues that you ran into.